Optimization is one of the most important applications of the derivative. For example, let's say we have a mathematical model for the demand given the price of an item, and we want to maximize the revenue. Or maybe we have a certain length of fencing and we want to enclose the maximum area. Or vice versa, maybe we have a certain area that we want to enclose with the minimum amount of fencing. Or maybe we have a mathematical model for the trajectory of an asteroid, and we want to find the minimum distance that this asteroid will come to Earth, right? So there are a lot of applications where we want to optimize something, which just means that we want to find the maximum or the minimum of a mathematical model. So today we're going to start talking about maxima and minima. Now, maxima and minima, those are just Latin pluralizations for maximum and minimum. And the points where the value of the function is largest or smallest are referred to as extrema. Those are just the extremes of the function. And there are a couple different kinds of extrema. There are absolute extrema, and there are also local extrema. Okay, so let's take a look at this graph shown here. If we go from left to right, you can see the function decreases until we hit a certain point, and then it starts increasing again, right? And this point where it stops decreasing and starts increasing, right? That's a local minimum, right? Because it's lower than any of the points near it. And then the function increases and increases until we get to this point where it starts decreasing. And this point would be a local maximum because it's higher. The value of the function is higher than any of the points near it. All right. Now you can see that those are not the absolute minimum and maximum of the function because there are points that are higher or lower than those local minima and maximum, right? So if you can see the next point here, this appears to be the absolute minimum of the function because if I look at the function as it's shown anyway, it appears that that point is the lowest point on the whole graph, on the whole domain of this function, right? So we would refer to that one as an absolute minimum. And over here, it looks like that point is higher, right? The value of the function is higher than any point on the whole domain of the function. So we would refer to that as an absolute maximum. Okay, so there's a more mathematical definition of absolute maximum and minimum and local maximum and minimum below, but I think it's pretty intuitive, right? So the absolute maximum or minimum are the points that are either higher or lower than any point in the whole domain. Whereas when we're looking for local maximum or local minimum, we're just looking at a small interval near that point, right? We're looking at a small interval near that point, and we're looking for the points that are lower than any of the points near it or higher than any of the points near it, okay? So, but let's go ahead and look at this first example here. In this example, we're asked to identify the location of the absolute and local maximum and minimum if they exist, okay? And we're going to assume that the domain of these functions is all real numbers, so it goes from minus infinity to positive infinity. All right, so these functions keep going. They're not on a bounded interval, right? Not on a bounded domain. All right, so if we look at this function, we want to find the local maxima. Let's find the local maximum first, right? So we come along here, you can see it's increasing, and you can see this point appears to be higher, right? The value of the function is higher than any of the points near it, all right, in a small interval near it. So I would call this point, which the coordinate pair, the x and y coordinate pair are negative 1, 2, right? Because when x is negative 1, it appears that the function reaches a maximum of 2, right? It increases to 2 and then decreases after that, okay? And then there's a local minimum here, right? Because at this point, the function is lower than the value of the function is lower than any of the points near it. So we can say that there's a local minimum at 2, 0. Oops. All right, and then, okay, so now we want to find the absolute maxima. Well, it looks like if I just, it looks like the function just keeps increasing and increasing as x gets larger and larger, and it looks like it's increasing to infinity. So I would say that if this function is defined on the open interval from infinity to minus infinity, then I would say that there's no local maximum, right? Because it just keeps going and going, and if I pick a point, I can always find a point higher. And the absolute minimum, well, if you go the other direction here, the function just keeps decreasing, and it doesn't seem to it seems to decrease to infinity. So I'm going to say that there's no local minima either. Okay. Now let's look at the next one. Again, we have a function that's defined on an open interval from minus infinity to infinity, and it looks like we have a couple of local maxima, right? Because you can see at these points here. Oops. Okay. At these points here, the function increases until it doesn't, and then it starts decreasing. So we have a local maximum at 1, 3. Oops, jeez. 1, 3. And then we have another one over here at 4, 3. Right, so we have 2 local maxima. And then we have a local minimum here, right, where it's lower than any of the points near it. So I'm going to say that that's 2.5, 2.5, 0. Okay, so that point is lower than any of the points near it. All right, now as far as absolute maxima go, you can see that we have 2 of them in this case, because the function reaches its highest point of 3 at 2 different points, right? The highest point on the function is 3, and it happens twice. So we actually have 2 absolute maxima. We have the same points we had before. It's the 1, 3 and 4, 3, right? We have 2 local maxima. And then we have let's see, then absolute minimum. What do we do? Is there any absolute minimum? You can see that, we have the local minimum at 0, but you can see there are values on the function where the function is lower than 0, right? And it seems like it just, the function, whether I go to positive or negative infinity, is just going to go to negative infinity. So there's no local minima. Okay. All right, one more here. Now, local maxima. Well, you can see this point is higher than any of the points near it. So we're going to call that point at 0, 5. That is a local maxima. Now, the local minima, you can see that it doesn't appear that it appears that there's an asymptote at 0, but it's never actually going to reach 0, right, if it's an asymptote. So even though there's sort of a floor to this function that doesn't go any lower than 0, apparently from what I can see from the graph, it never actually gets to 0. And so we can get closer and closer to 0, but there's no local minimum, even though the function doesn't go any lower than 0. It never actually gets there, and it just gets closer and closer to 0. So if we pick a point on the function, we can always find a point lower than it. All right, and then the absolute maximum then is the same, 0, 5. You can see that doesn't appear to be any points higher than that. And then the absolute minimum, again, is just none, right? We don't have any local minimum, right? So, oops, none. All right, stay. All right, well, I'll meet you in the next video for the next example.